Hey guys, this video is about applying the integrated rate laws. To answer the question, so that you can determine how much of the reactant concentration is there at a given time. So, if you haven't watched the previous video, the first video on the introduction to the rate laws, you should do that first. This is one on applying the rate laws. Let's say you have a substance called cyclobutane. It's C4H8. That's 4 carbons connected in a ring to each other, surrounded by hydrogens. Now this substance decomposes readily to 2 molecules of C2H4, 2 molecules of ethene or ethylene. If you know that this is, for example, a first order reaction, you're told it's a first order reaction, then we would use the first order rate law to determine how much of the reactant is left over at a given time. So let's say we have an initial concentration. Let's say the initial concentration of C4H8 is equal to 2 molar, 2.00 molar. And what you want to know is after a certain time, after let's say at time is equal to 0.010 seconds, after that time, how much of the cyclobutane is left over? Well, the first thing we do is we realize that as a first order reaction, we use the first order integrated rate law, which is expressed as the natural log of A naught over A at times T is equal to K times T. The other thing we're going to need to know about this, of course, is the rate constant. And you are given that information. You're told that the rate constant is 87 seconds to the minus 1. So if you look at the information that you have, this right here is the initial concentration. This is the A naught. And what we're ultimately solving for is A at times T. If we plug into the first order integrated rate law, we have the natural log of 2.00 divided by what becomes our unknown, right? The concentration of C4H8 at times T. And that's equal to 87 times 0.010. There's a couple ways we can approach this, but let's see. If we expand this expression out, the natural log of 2 over the C4H8, if we expand it, becomes the natural log of ln of 2 minus the natural log of C4H8 at times T. And that's equal to 0.087 now, if we move the decimal 2 places to the left. And this, of course, is an application of the natural log of A over B is equal to the natural log of A minus B. So that's what we've done here. We've separated this out, which means that minus the natural log of C4H8 at times T is equal to 0.87 minus ln of 2.0. Let's bring the negative sign over. So the natural log of ln C4H8 at times T is equal to minus 0.87 times the natural log of 2, which, when you put that into your calculator, is equal to about minus 0.18. Now, in order to undo the natural log, we bring both sides to the e power. We raise both sides to the e power. So e to the natural log of C4H8 at times t is equal to e to the negative 0.18. E to the ln of x is equal to x. So therefore, e to the ln of C4H8 is equal to C4H8 concentration at time t. And e to the negative 0.18 is 0.84 molar. So what that tells us is that after this 0.010 seconds, we have 0.84 molar. That's the concentration of cyclobutane that's left over. Looking back at this reaction, because for every 1 mole of cyclobutane that decomposes, we get 2 moles of the ethylene gas, that means that at times t, if what we also wanted to know was what's the concentration of the ethylene gas at this temperature, it would be twice this number, twice that, because the rate at which that disappears is equal to twice the rate at which the product appears. This is the final answer, and there's your example of how to use the integrated rate law. We're going to do one more in another video about how to use it specifically for half-life.